Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Count the number of houses at a certain distance to. The problem is a bit hard, but as always, we will start from a smaller version of the problem and incrementally add constraint and finally arrive at the final solution. So if you stick till the end, I'm very sure you will be able to understand this problem as well as the thought process that you can use while solving similar problems in future. So with that, let's get started. The problem states that you are given three integers n, x and y. N denotes the number of houses that you have connected by n streets. The streets are connecting house number 1 to house number I plus 1 for all I between 1 and n minus 1. So these are n minus 1 streets which are connecting house 1 to house 2, house 2 to house 3, house 3 to house 4 and so on and so forth. Now the final street connects house number x to house number y. Now given this network of houses, we need to return a n-sized array where result of k will denote the total number of pair of houses such that the minimum streets required to reach one house to other is k, right? So let's take an example. Let's say this is the pair of houses. N is 3, it means there are 3 houses. Now there will be 3 streets as well. First street from 1 to 2, second street from 2 to 3 and finally third street from x to y, which is 1 to 3. Now here you have to figure out this array where first one denote how many pair of houses are there which are at a distance of 1, how many pair of houses are there which are at a distance of 2, and finally how many pair of houses are there which are at a distance of 3. So in this particular scenario, the shortest path between every pair of house is 1. So from 1 to 3, the shortest path is 1, not 2. You can go from 1 to 3 in two ways. You will first go to 2 and then to 3, or you can directly go to 3. You will take the shortest path because we have to find the distance or the minimum distance between one house and the other. So from 1 to 3, we require just one street. Similarly, from 1 to 2, we require one street. From 2 to 3, we require one street. And finally, from 3 to 1 as well, we require one street. So overall, there are 6 pairs. For each of the pair, the shortest distance between those two houses is 1. And hence, the first value in this array is 1. That is, there are 6 pair of houses which are located at a distance of 1. And the other 2 will be 0 because there are no pair which are located at a shortest distance of 2. Similarly, there is no pair of house which are located at a shortest distance of 3. So let's just take one last example. Let's say this is the network of houses. We have n is 5, it means 5 houses. Network is 1 to 2, 2 to 3, 3 to 4, 4 to 5, and finally from x to y, which is 2 to 4. Now in this case, again we need to return this 5-sized array. First one will denote how many pair of houses are there which are located at a distance of 1, at a minimum distance of 1. How many pair of houses are there which are located at a minimum distance of 2, and so on and so forth. So let's just figure out this one. How many pair of houses are there which are located at a minimum distance of 3. So if you look at it, from 1 to 5, you can either take this path or you can take this path. So going from 1 to 2 and then from 2 to 4 and then from 4 to 5 is the shortest path to 5. So from 1 to 5, we will have distance equals to 3. Similarly, from 5 to 1 as well, the distance will be 3. And these are the only 2 pair of houses which have a shortest distance of 3. You take any other pair, the shortest distance will not be 3. For example, if you take 2 and 5, shortest distance is 2. You will go from 2 to 4 and then from 4 to 5. So in total there are just 2 pair which have a shortest distance of 3, and hence the third value in this array is 2. So you will similarly fill all other values and return that as a result. So hope the problem statement is clear. Now how to solve this? There are various things in the problem. So I would say, instead of solving this problem directly, let's try to tackle a smaller version or reduced version of this problem. Let's say this x2y doesn't exist at all. In other words, x is equals to y, and we have to solve the exact same problem. So x is equals to 5, it means there is a road from 4 to 4 or 5 to 5 or something, which means that there is no extra road at all. What roads you already have, that from 1 to 2, 2 to 3, 3 to 4, these are the roads which are able to take you from one house to other. All the other roads which exist doesn't matter, because that road will take you from house number x to house number x itself, so you will never take that road, right? So if you haven't solved this version of the problem yet, I would encourage you to pause and try to solve this version of the problem by yourself. So hope you have thought about it. We have the houses connected in linear fashion. So 1 is connected to 2, 2 is connected to 3, 3 to 4, and so on and so forth. Now we need to fill this array. Notice there will be no house which are at a distance of 10, because they are at least connected by adjacent edges. So maximum distance will be 9. So the value of 10 will be 0. So that's why I removed 10 completely. We need to just fill these 9 values. Now let's start from the beginning, from 1. So what is the shortest distance from 1 to 2? The answer is 1, because you can go from 1 to 2 in just one house. Now what is the shortest distance between 1 and 3? The answer is 2, because there is no other path at all, there is just straight paths. So from 1 you have to go to 2, and from 2 you will reach 3, right? So similarly, what is the shortest path from 1 to 4? Again 3. So what we are doing, we are saying we found a pair that is at a distance of 1. So we'll increment 1 here, or you can increment 2 here, because if 1 to 2 has a distance of 1, 2 comma 1 will also be at a distance of 1. So for now we are just trying to figure out the pair h1 comma h2 such that h1 is less than h2, and finally we will just multiply the answer by 2 to take care of the other pair as well, h2 comma h1 as well, right? So for now we have to figure out the distance from 1 to 2, 1 to 3, 1 to 4, and so on and so forth up till 1 to 10, and then 2 to 3, 2 to 4, 2 to 5, all the way up to 2 to 10, and then 3 to 4, 3 to 5, all the way up to 3 to 10. So we are starting with 1. So from 1 to 2 we know it has a distance of 1, so we incremented the value at position 1, that is we found a pair which is at a distance of 1. From 1 to 3 the distance is 2, so we'll increment this particular value. We found a pair of house that are located at a distance of 2. From 1 to 4 we'll increment 3. Similarly from 1 to 5 we'll increment 4, and then we'll increment 5 for 1 to 6, 1 to 7 we'll increment 6, 7, 8, and finally for 1 to 10 we found a pair of house which are located at distance 9. So that's what we will do for house number 1 as the starting point. Now once you have done this, let's tackle house number 2 as the starting point, right? So we are starting from 2. So from 2 to 3 we found one house, so we'll increment 1 by 1. From 2 to 4 we found one pair which is at a distance of 2, so we'll increment position 2 by 1. From 2 to 5 we'll increment position 3 by 1, and so on and so forth all the way up till 8. So from 2 to 10 the distance is 8, so we increment the position 8 by 1. We found one pair of house which are located at distance 8. right? So all of these will be incremented by 1. Now for 3, what will happen? The same thing, right? We will start from 3 to 4, 3 to 5 and increment these values. So afterwards, whatever will be the total value at each position, we will multiply entire thing by 2 and finally we will get our result, right? Why multiply by 2? Because we considered from 1 to 2, but 2 to 1 is also needed to be considered, and hence everything will be multiplied by 2 at the end. So this is a valid solution. What will be the time complexity of this entire solution? What we are doing, we are starting from a particular index I, and then for each index I, how many such indexes are there? Total n such indices can be there, right? Now for each index I, let's say this is I, what we are doing, we are iterating over all the indexes in the right. We are finding out what is the distance between 3 to 4, what is the distance between 3 to 5, 3 to 6, and so on and so forth, and thereby incrementing these array as well. So this iteration can also take all the way up to order n. So overall the complexity is order n square, which surely will not pass because n is 10 power 5. So we have to optimize this, but this is a valid solution. Now how to optimize this? Notice what we are doing. We are saying that, okay, if we start from 1, we will increment 1 at position 1, we will increment 1 at position 2, we will increment 1 at position 3, increment 1 at position 4, so on and so forth, all the way up to increment 1 at position 9. So what we are doing, we are incrementing 1 in the range 1 to 9, right? Similarly for second position, what we are doing, incrementing 1 at position 1, incrementing 2 at position 2, incrementing 3 at position 3, and so on and incrementing 1 at position 2, incrementing 1 at position 3, and similarly incrementing 1 at position 4, and finally incrementing 1 at position 8. So again we are incrementing 1 in the range 1 to 8 for index 2. And if you look at and continue in the same fashion, you will see that you will be incrementing 1 at index 1 to 7 for 3, and so on and so forth. So now instead of incrementing these values one by one, if you can apply any range query data structure, you will be able to increment or get the final increment done in just log n time, right? So instead of iterating over this array and then incrementing every position by one by one, instead of this you can simply do a range query, use a range query data structure and increment everything or arrange L2R by 1 in just login operation. So for each position you will be doing a range update which will take you login time, and your overall complexity will be n login, which is sufficient to pass the given time constraint. Now this is one way where you can use range query data structure. You can use segment tree. If you don't know about segment tree, I have a video on segment tree from scratch. We have a complete series on that. You can watch that. I will link that in the description down below. But in this particular case, there is a catch. The catch is we don't need the value at a particular index in between. We need these values at the end when we are finally preparing the result, right? And now because we don't need to query the values in between, instead of doing a range, applying a range query data structure, we can simply take the advantage of prefix sum to tackle this. So what we will do is, we know that we need to increment 1 in the range 1 to 9. So we will increment 1 at the first position and decrement 1 at the 10th position, right? and then once if you apply a prefix sum over this array, the first position will be 1, second position will be 1, it will be 1 1 1 1 1 1 1, and finally this will be 0. So basically the idea here is when you apply prefix sum, this 1 will be propagated all the way to its right, and this -1 will also be propagated all the way to its right. So in this part of the array, what is propagating? 1 plus -1, which is 0. So this part of the array remains as it is, and this entire part will get 1, and that's what we want, right? So this we are able to apply this trick here because we don't need the value at a particular index, let's say value at 5 in between. If you need that, then there's no other choice, you have to apply a range query data structure. So this all things are explained in the segment tree basic video, you can refer to that. In this case we don't need to apply segment tree or any range query data structure, and instead just use prefix sum at the end when we want to find the answer. So incrementing 1 in the range 1 to 9 will simply mean incrementing the value at 1 and decrementing the value at r plus 1. So it will be simply order 1 operation. So the overall complexity is just order n. So hope this until this point everything is clear. So we now are able to solve the given problem in order and time where x is equals to y. In other words, there is no extra road or extra useful road that we have. Only roads we have is linear roads, right? So the pseudocode for this would be very straightforward, as we have discussed. We'll just go from 1 to n and simply increment 1 in the range 1 to something, and that something is n minus I plus 1, n minus I, and because we have to increment 1 in the range 1 to n minus I, what we will do, we will increment 1 at this index, right, and we will decrement 1 at index greater than this. So n minus I plus 1 we decremented, right? So after you have done this, at the end you will just take the prefix sum of this psum array, and that will be your answer, right? So hope this part is clear. But the original problem states that x may not be equals to y. So how to tackle that now? X is not equals to y, it means there is one extra road that can be used, and if you use that road, things can change drastically. For example, in this case, if you start from 1, previously from 1 to 9 you have to traverse 8 roads, from 2 to 3, 3 to 4, 4 to 5, 5 to 6, and so on and so forth. But now you can go from 1 to 2, then from 2 to 3, and from 3 you can take this shortcut and reach 9 directly, right? So see, things have changed drastically now with just one extra road. How to tackle this? So look at this. This extra road can be used by which all elements? It can be used by these elements for sure, because for these elements, to reach any of these elements, this road will be helpful for sure. Instead of traversing these many elements, you can just take this shortcut and reach the other node, and it will help you. For these nodes, will this road help? The answer is maybe or may not be. For example, for 4 it may help. You can go to 9 in this direction instead of going to 9 in this direction, right? So it may or may not help. But what about 9 and 10? Will this road help? The answer is no, because this road connects two houses which are before y, right? So after y, any houses that are exist, this road will not be useful for them, because after y what you want is how many houses are there, how many houses of pair h1 comma h2 are there which are at a distance of k, where k is in the range 1 to n. Now if you are considering h1 as greater than y, then h2 automatically will be greater than y because of the definition, because we are considering only the pairs which are h1 where h1 is less than h2, because the other pair we will just multiply by 2 at the end. So we are only considering this pair for now. So for if the source is greater than equals to y and destination also is greater than equals to y, there is no point in using this road at all, right? So hope this point makes sense. Now because in this kind of scenarios using this road doesn't make sense, for everything greater than y you can simply apply the algorithm that we have just discussed, right? Basically this algorithm for everything greater than y, greater than equals to y. So for everything greater than equals to y you can still do the same thing. Now we have taken care of these all elements. Now remain these elements, right? What will be the effect of this road on this remaining elements? Now notice two things. One, for these elements this road will help in getting to a position which is greater than the current one by going forward. But for these elements, or for some of these elements, we can use this road by going backward as well, right? So clearly there are two distinct use of this road. One, the forward use, wherein you will only go forward and use this road as a shortcut to the other node or other house. Second use is you want to go from 4 to 9, but instead of going only forward, because you know there is a road or there is a shortcut from 3 to 9, you will go backward first and then from 3 you will reach 9, right? So there are two different use of this road. So let's segregate them as well. Let's say we now only care about the houses which are less than or which exist before x, and second condition is the houses which exist between x and y. So we'll solve for these two things differently, because overall we see that the way this road can be used in these two criteria can be different, right? So let's talk about the first criteria, which is the house that we are considering is less than equals to x. In other words, for we wanted to find out how many pair of houses are there starting at index 1 which are at a distance of k for all the k between 1 and n, right? So we want to fill this array for house 1, or where house 1 is the source, right? We want to fill this array where house 2 is the source, so on and so forth up till house x minus 1 is the source. So for all of these we know that the use of this road will be very similar, and for everything in between the use of road will be different, so we'll take care of them differently. So now we want to find out, we want to fill this array for these all houses, right? So how it will happen? So we are considering all the houses or all the I which are less than equals to x for now. Let's say I is 1. So you want the shortest path to every node from 1, right? How to find shortest path? You can either apply the extra or you can apply BFS here, because the graph is equated. Every edge has a weight of 1, so graph is equated, so you can apply BFS directly. So I applied BFS already. You from 1 you will go to 2, 2 to 3, and from 3 there are two choices, either to 4 or to 9, right? And then so on and so forth. So what does this mean? This means from 1, if you want to go to 5, you will take this route. From 1, if you want to go to 7, you will take this route, right? So what you notice here? Notice that from 1 to 6 everything is intact. What you had previously is something you had now as well. So previously from 1 to 2 you were following this path. From 1 to 3 you were going from 1 to 2 first, and then from 2 to 3. 1 to 4 again you go from 1 to 2 and then 2 to 3 and 3 to 4. So up till 6 everything is intact, and after 6 things have changed drastically, right? So we can say that up till a point P everything is constant, or basically what we have been doing so far, where I is the source and destination can be anything less than equals to P. We can simply apply the same thing, basically increment 1 in the range 1 to some x, right? So that part is constant. Now after P things have changed. Now first of all, why did this happen? This happened because up till a certain point it still makes sense to follow the straight road, right? But after a certain point P, it may happen that if you take this shortcut and then start coming backward, you require less number of hops to reach a particular node than to only come forward by following the straight roads, right? Because of this criteria, up till a point P straight road will be optimal, but after a point P you will say, okay, I will always take this route and then come forward or backward depending on what is my destination, right? So let's say you know point P somehow. How to arrive at point P is different question, but you know point P. So you know up till point P everything will be same, that is from 1 to 2 you require, or there is a one pair which is a distance of 1, there is one pair of house which is at a distance of 2, there is one pair of house which is at a distance of 3, all the way up to P minus 1. So let's say this is P, so all the way up to P minus 1 we know that there is one pair of house which are at a distance of 1. Now after P we know that we have to take this route for sure, because that will give us the optimal value, right? So you can completely ignore all the routes in this range now, because you know optimal route will go from 3 to 9, right? So now what you can do is, you are sure that you will reach 9, you will take this path for sure, right? So let's take this path. If you take this path, you have already considered, or you have already taken 3 streets to reach at Y. Now once you are at Y, for everything after Y you will just require 3 plus 1, 3 plus 2, 3 plus 4 and so on and so forth, right? For everything before Y up till P as well, 3 plus 1, 3 plus 2, 3 plus 3 and so on and so forth, right? So now what you will do is, instead of incrementing 1 in the range 1 to something, you have to increment 1 in the range 3 to something. Why 3? Because starting distance at Y to arrive at Y will be 3. You have to visit 3 different streets to arrive at Y. Now this 3 plus how many more nodes are there, that's what you will be visiting, right? Similarly, let's say there are 2 nodes, so you will say I will add 1 in the range 3 to 4, right? And similarly I will add 1 in the range 3 to, how many nodes are there before this? 2, so 3 to 5. And notice, because you have to consider Y only once, you can either make it 4 to 5 or keep it 3 to 5 and make this one 4 to 4. That's your choice, right? So let's assume that we have arrived at point P by some magic. After that everything is straightforward. You for a single node you have to now, instead of doing one thing, that is incrementing 1 in the range 1 to something, you will now do 3 things. You will increment 1 in the range 1 to P minus 1, right? you will increment 1 in the range 3 to something, which something you can count the number of elements here and you can add it to 3, and that will be your right bound. And similarly you will add 1 in the range 4 to something, which again can be figured out by using the number of elements in the left, right? So for a single element you are now doing 3 distinct increment operation, which is fine. Previously you were doing one increment operation, you are now doing 3 increment operation. And increment operation we already know how it is. Just do p of l plus plus and just do p of r plus 1 minus minus, right? So increment operation is not an issue. You can do 3 increment operations as well and everything will still be fine. The complexity will not affect much. So you will, that's it for 2. In the same fashion you will do for 2 as well. Sorry, that these all things are for 1 when I is equals to 1. Now the same thing will have to do when I is equals to 2. For this again you will find some point P. This point P may or may not be same. Once you have find the point P, you will apply these 3 disjoint operations to cover all the houses in the right? So what is the point P now? Or before that, let's just look at the pseudocode one more time. The pseudocode would look something like this. Let's assume you know what is the point P. I am representing point P by M here in this pseudocode, and why we are representing with M, I will come to that. So let's assume that this P is equals to M, right? So what we have to do, we have to increment 1 in the range 1 to P minus I plus 1, right? These many number of elements are there. So if you remember the previous thing, we were incrementing 1 in the range 1 to n minus I plus 1, where we said that all the way up till n we will follow the straight path, right? But now we are saying only up till P we will follow the straight path. So we'll increment 1 in the range 1 to P minus I. Now once we took care of everything between I and P, now we know that we have to take this route for all other elements. There is no other choice. So this piece or these many number of streets will always be there, x minus I plus 1. X minus I will denote number of nodes to reach x, and from x to y there is one more road, so this is plus 1. Now you will always need these many roads to reach any further. So now you arrive at y. From y all the way up till the last one, if you need 3 nodes to arrive at y, for y plus 1 you will need 4, for y plus 2 you will need 5, and so on and so forth. So basically you will add 1 in the range always to always plus y minus p, and always plus 1 to always plus n minus y plus 1. So this is the right side and this is the left side, right? So once you do this, you will be contributing, or you will be taking care of all the all the houses, all the pair of houses that is starting at index I and ending at any other house which is after I. So once you have done this, your final p sum array would contain the values, and you will simply do the prefix sum and return that as an answer. So if you remember, we divided the problem into 3 parts. First, everything after y. For that we know how to do or what is the value. We can use the exact same thing. Then we say everything before x. For that we say that this is the algorithm, that is everything between 1 and x. Now one more thing is remaining, which is everything between x and y, right? So what if the starting house is between x and y? So before coming to that, let's just discuss about point P. So what is the value of point P? Point P will be the middle element. Why? Because if you think about it, you are going from one node to another in a straight line, right? Let's say there are 5 nodes in general, and there is a path from first to the last node. Now when will you use this path? You will use this path only when the path in the forward direction is longer, right? So in this case, up till here or up till the middle point, there is no point in using this path, because up till the middle point, if you take this path and then come back, you will take m number of edges here plus one edge, because you are taking this path. Whereas if you come only forward, you will take less than or equals to m number of edges. So this forward path will always be beneficial if you are arriving at a point which is at the middle or before the middle. But once middle is crossed, let's say up to here, so if you take this path, you will be visiting greater than m number of nodes. Whereas if you come in the backward direction, because it is after midpoint, this path is less than m, and you have one more, so whatever value you will get will be less than equals to m, right? So it's always makes sense to come from the backward if you are considering a node which is after the midpoint, right? So p would simply be the middle element, right? So we now have solved for two different parts of the array, one everything after y, one everything before x. Now comes everything between x and y. So if you have watched till this point, it's I think you will have some thought about how to solve this particular part. So just try to pause the video and come up with the algorithm for solving for houses between x and y by yourself. So hope you at least give it a try. The solution is exactly similar. So what we will say, we'll say okay, let's try out one of the I. So we say I is currently 7, so we just try shortest path algorithm from I to figure out how the shortest path will change. So from 7 we apply BFS, so we go from 7 to 6 and 7 to 8, and then from 8 we go to 9 and so on and so forth. Basically whatever edges we have, we just do the simple BFS. So from 7, what all things we care about? 7 to 8, 7 to 9 and 7 to 10, right? So for all of these we can see everything is exactly similar, as if nothing happened, right? Even though this road exists, we are still following the linear path all the way up to 10, right? So what does this denote? This denotes that for 7 we can use the very first algorithm, that is linear path algorithm, without worrying much. That is, we'll increment 1 in the range 1 to 4, and then 1 to 3, right? And then for 8 we'll increment 1 in the range 1 to 2, and for 9 we'll increment 1 in the range 1 to 1, right? So this is what the linear path algorithm was. So we can follow this for 7. There is no issue with that. So let's take if you take 8 as well, you will see the same is true. Now let's take 6. If you take 6, again you will see exact same thing is true. You can still follow the linear path algorithm without any issues. Things become interesting when you go beyond 6, when you go to 5, 3 or 4. Here if you look at from 5 all the way to 8, you are following one path, and after 8, that is 9 and 10, you are following something else, some completely different path, right? In the same fashion, when you are at 4, you are following some path up till 7 in the straight fashion, and after 7 your path will now completely change based on some criteria, right? So the same is true for 3 as well. So why this happen? Again, the exact same reason. You have some nodes in consecution, right? And you are attaching first node to the last node. Now if you want to go from this node to anything afterwards, you will follow the straight path only when you are in the first half of the array. For the other half, you will not follow the straight path, instead you will go backward and then come forward, right? So if you look at it, the middle part is still 6, right? So up till 6, if you want to go to 7 or 8 or 9, you will still follow the forward path. You will not say, okay, I will go backward to 3 and then from 3 I will go to 7, 9. Why? Because to go to 3, the number of edges required will be greater than equals to m, because we are saying that the point we are considering, or the value of I we are considering, is after middle, right? So I is greater than equals to m. So in this kind of scenario, if you go backward, you will have to visit at least greater than equals to m number of edges, and then you have to visit one more edge, and then you will do something to come to the final destination. So you are visiting greater than m plus 1 edges, whereas you can simply go in the state format and you will arrive at the destination in less than equals to m number of edges. How? Why? Because you are in the middle, so to go to the extreme right as well, you will need at max m number of edges, right? So that's basically the trick. Basically everything up till middle, you don't care about going back and then coming forward. That you will not do, because you know that is not optimal. So again, for everything between x and y, you will come to the middle point. For everything after m, you can apply the linear path algorithm, right? For if I is less than m, that is 3, 4 or 5, then you have to think a bit, because now if you want to go to 9, instead of taking this route will be shorter, right? Because of same argument. Now what exactly you will do for, let's say 5 or 4? Notice for 5 what you have to do, or what you have to figure out: the distance to 6, distance to 7, distance to 8, 9 and 10, right? That's what you have to figure out for 5. And similarly for 6, you have to figure out distance to 7, 8, 9, 10, and 4 as well, distance to 5, 6, 7, 8, 9, 10. So not all the distances you will follow the reverse path, because if you go to 6, if you want to go to 6, why will you come back to 9 and then come back to 6? You will not do this, right? Instead you will directly go to 6. Similarly, if you go to 7, if you want to go to 7, you will still follow the forward path instead of going all the way to 3 and then coming back to 7. Now when will the reverse path be helpful? Again, after m by 2 number of points, right? Or after e by 2 number of points, where e is the size of the cycle. So after you have visited e by 2 points, if you visit further in the straight path, you will require greater than m number of edges, right? Whereas if you go backward, you will require less than equals to m number of edges. So hence, up till n e by 2 number of nodes, you will follow the forward path. After e by 2, you will follow the backward path, right? So that's basically the algorithm. So for everything, you will first figure out, let's say, a value p, right? So for this I, this will be p. Once you have figured out this p, you can apply the straight path from I to p, and for everything after p you will say I will go backward and then come to y, and from y I will calculate everything after p. So if you are at y, let's say p is here, right, you have some elements here, and let's say n is here, so you have some elements here as well, right. So you are at a particular index I, so you said I will go backward to x, from x I will go to y. Okay, now once you are at y, you will calculate everything with respect to this path in all these values. So for y, if the value is, let's say 4, you require 4 edges to come to y. So 4, you have found one house at a distance of 4, you will have found one house at a distance of 5, you will have found one house at a distance of 6, you will have found one house at a distance of 7, and so on and so forth. Basically the exact same thing that we have been doing with I less than equals to x when we know the point p. So once you have figured out this point p, you can do the exact same thing, right. So how will the pseudocode look like? The pseudocode will simply be this, where okay, we have to also do p minus minus or p plus plus every time, right. So notice for all the way up till m, going backward doesn't make sense, because number of nodes after m will be less than equals to m. So going backward doesn't make sense, so we first figured out this m for us, right. So this p is different, right, we first figured out this m for us. Once we have figured out them, from m to y we will simply apply the linear path algorithm. So from m to y we will simply say p sum of 1 plus plus and p sum of y minus I plus 1 minus minus, right. Now after that we need to now consider everything from x to m, right. So this will be not inclusive. So for each index, let's say this is I, for this index you need to first find out a point p up till which going forward is best, and after which going backward is best, right. So for the first index x, point p will be m for sure, because that's the middle point, right. You will pick that point with a distance of e by 2, and distance of e by 2, m exists at a distance of e by 2. So for point I, the point p, when I is equals to x, point p would be m. So once we start with x, and for x we find out the p. Now once we have p, for everything between I and p we will apply linear path algorithm, that is from x to x plus 1 distance is 1, x to x plus 2 distance is 2, x to x plus 3 distance is 3, and so on and so forth up till point p. So from I to p we will apply linear path algorithm. Now once we have crossed p, we know that we will go backward all the way to x, and from x will come to y. So how many nodes are required to go to x? From I minus x number of nodes, and from there we followed one more edge to come to y, so plus 1. Now once you have these many nodes or these many streets visited to come to y, after reaching to y you will simply say I have found one house at a distance of always, I have found one house at a distance of always plus 1, I have found one house at a distance of always plus 2, one house at a distance of always plus 3, and so on and so forth. So basically you will increment 1 in the range always comma always plus something, right. And what is this something? This something will be denoted by number of nodes that you have. in this case number of nodes is y minus p before, right? And similarly afterwards as well, you will start from always plus 1 because y you already considered, so now it's time from y plus 1 to all the way up to n. So y plus 1 will be at a distance of always plus 1, so you'll start from always plus 1 and go all the way up to the right hand side, which is at a distance of n minus y plus 1 plus always. So after doing all of these, you will increment p as well, because once your I will be incremented, p will also shift, right? So that's what you are doing. So that's the entire algorithm. So let's just do once a recap of the entire solution and then we'll look at the code. So we started off with figuring out the solution for x equals to y, and for x equals to y we saw that if there is no random paths or there is only straight path, you can simply apply increment operation or in a single range to get the final result. So but the problem has asked us when x is not equals to y. So we divided this problem into 3 parts. First, where this, because we know how to solve for straight paths, we are biased toward making this problem converted into something which is related to a straight path, right? So we saw that okay, everything after y, this path will not be useful at all, because once you have crossed y, from y you want to go to y plus 1, y plus 2 all the way up to n. Similarly from y plus 1 you will go to y plus 2, y plus 3 all the way up to n, right? So after y, this path will not be useful. Hence you divided this problem into 2 parts, one which is after y, and after y you will apply the linear path algorithm, and one which is before y. Now for before y as well, there are 2 cases. One where you will go backward and then come forward, right? And second where you will only go forward. So that we divided into 2 parts, one where I is less than equals to x, and second where I is between x and y. So for I between which is less than x, we saw that up till a certain point p everything is linear, and after a certain point p we have to take this path and things started to change. So what is that point p? It will be m, because after the middle point the number of edges that you need to visit will be greater than m, or the number of nodes by 2. So after middle point you will always want to take this shortcut and then come backward, right? So that's what we have done. We figure out the point p, which will be equals to the middle point of x and y, and once we have figured out the point p, everything from I to p will be straight, and after p we have to take this path and we have to reach y, and from y we'll go backward and forward, right? So everything up till p is following a straight path algorithm, and after that we know that we will have to take this route. So this route we calculated what is the number of edges that will be there in this route, and once we have the route we simply follow that route and go backward and forward depending on how many numbers are there in the front and how many numbers are there in the back. And finally for x between x and y, we saw that up till a certain point, or rather the middle point, it doesn't make sense to go backward and follow this path, because to go backward itself you will require greater than equals to m number of edges, right? So it doesn't make sense to go backward up till after point m. So after point m you will use the straight path algorithm. Now once you have crossed point m, let's say you reached some point I which is before m, so for that there will be a point p up till which you will have shortest path algorithm or shortest path way to reach everything between I and P, and after point P you will go backward and then take the shortcut. And why this is the case? Because this cycle is of, let's say, length n. So everything up, or let's say this cycle is of length m. So if you are considering any node in the next m by 2 nodes, you will be taking the forward path, because in that case you will be visiting less than m by 2 number of edges. Whereas if you are considering any node after m by 2, you will instead take the backward and then come forward, and then take this shortcut and then come backward, right? So that's what we did. For every node I, we figured out a point P up till which everything will go in the forward direction, and after that, for everything after y, we simply apply the algorithm that we have used for I less than equals to x. That is, if it is, we know that we will be coming to y, so we figured out how many node or how many edges we will be visiting to come to y, and after coming to y we just figured out how to go from y to everything in the right and how to go from y to everything in the left. Okay, so hope this entire session makes sense. If you have watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself. So this problem is not implementation heavy, it's just how you approach the solution. So next we're looking at the code. The code is exactly what we have discussed. We have removed two criteria where x is y and x plus 1 is equals to y. Basically in these two criteria there is no new edges at all, so we just simply apply the straight path algorithm and get the answer. For all other scenarios, we divided it into 3 halves, if you remember. First, greater than y, second, less than x, then third, between x and y. And x and y as well, we divide into 2 parts, everything after m and everything before m. So in other words, everything after m is one piece, everything before x is another piece, and between x and m is another piece. So everything after y, we did this, we figured out m. Now from m to y, we again did the straight path algorithm. Now for everything between x and m, we are figuring out point P. So this TO2 is the point P that we have been discussing in the solution. So once you have figured out the point P, we will simply apply the straight path algorithm up till point P, and after point P, we know we will be having to visit always number of nodes. So if you recall the pseudocode, we'll have to visit always number of edges every time, and we'll simply do always p sum of always plus plus and p sum of always plus y minus p plus plus. So that's what we have done. And finally, for the right side as well, we have done the exact same thing, right? So this is what for x to m. So we have figured out from y to n, m to y, x to m. So we have figured out, we have taken care of everything between x to n. Now from 1 to x, we have applied the algorithm that we have discussed for x to m, that is the straight path from 1 to m, right? From 1 to m or I to m, we apply the straight path algorithm. After m, we have to go follow the shortcut and then come back. So there are 2 paths, one after y and one before y. Sorry, one before y and one after y, right? So once you have applied this entire thing, you will simply do a prefix sum over this prefix sum array and populate your results. And notice you have to also multiply by 2, because everything that we have been doing so far, we have considered h1 comma h2 where h1 is less than h2. So we haven't considered the other case where h2 is greater than h2 is greater than or less than h1. that case will exactly be same, so we'll simply multiply everything by 2. That will take care of it. So hope this entire version makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.